So the last thing we talked about there was dimensions versus units. Again, dimension is something to be measured, something we want to measure, and a unit is a standardized quantity we use to be able to communicate those measurements with each other. Okay? Let me get a little bit organized here, if you'll pardon me for just a second. I guess I could have done this in between. This is lecture 1. Right? This is page 1. And lecture 1, 2. Right, we'll do lecture 1 and 2 together. Page 1 of lecture 1 and 2. Alright. So normally I'd build a table. Let's build this table here. Let's talk about some common units in dimensions that we would want to measure and use. We'll use 2 different unit systems in here in this course, in this textbook. Right? And I'll expect you to be fluent in both unit systems. So we have what we call the English units. Most of the rest of the world calls them either the American customary system, because we're about the only ones that use it. The English don't use them anymore. Sometimes it's called the imperial units. Any of those are okay. So dimension, we've mentioned the dimension being length. The SI base unit, of course, is the meter, but you might also have centimeters or kilometers. In the English units, we will use feet, inches, so 12 inches in a foot. Occasionally we'll use a mile, 5,280 feet in a mile, and I don't expect you to remember that. I always have to look that up until probably the last 10 years or so. So that is if length is our dimension, these are some units. Some other things, time. The base unit in both systems is the second, and that's the unit we will use the most of. In both systems, if we use fractions of second, it's going to be milli, micro, etc. We'll use SI prefixes for smaller quantities of time. For larger quantities of time, we'll use things like minutes, hours, occasionally days, but normally it's going to be seconds or hours are the common units we'll use there, regardless of which system. Let's see, what else? A couple of others. So we're going to talk about some other properties and some other dimensions today, but some common ones that you should be familiar with up to this point would be mass. So in the SI system, the base unit, of course, is the gram, or most of the time we will use the kilogram as our base unit. All right, there's some discussion we can have about which one's the base, but most of the time we'll use the kilogram as our base unit. In the English system, now this is LB with a subscript M. That is pound mass. Now, when I write it in cursive because I tend to write it very quickly. I learned in cursive. I understand they don't always teach that anymore, but this is my cursive L, B, and an M there. Okay. You will see some textbooks will use the slug. That's popular in a lot of mechanical textbooks, a lot of statics textbooks, and a lot of strength of materials textbooks will use the slug. We can talk about its advantage here in a second. In this text, we will use pound mass. It has some other advantages, and that's common in most thermal science courses like fluid mechanics, heat transfer, things of that nature. We tend to use the pound mass. Now, the base unit of force, of course, in the SI system, we use the Newton, named for Sir Isaac Newton, so it's a capital N. In the English or American customary system, we tend to use the pound subscript with an F as force. Again, if I'm writing that, that looks like this. Okay, the pound force. So this is my cursive LBF, and that's normally how I will write it. You'll get used to seeing it. My kilograms will look terrible, and my pounds will look terrible. Okay, we can talk about how those work here in just a second. Let's see what else we've got here. Yeah, I think that's actually where we're at right now. So remember, from physics, force, of course, is the product of mass, distance per time squared. I don't know why there's a space there, but that's just how it's displaying on my tablet. Mass, distance per time squared. Force is a complex dimension. It is a combination of multiple other dimensions. So if we talk about the Newton, right? So 1 Newton is the result of 1 kilogram being accelerated at 1 side there so I'm not putting my elbow on it. 1 Newton is the result of 1 kilogram accelerated at 1 meter per second squared. Okay? So what that means is that when I do conversion factors, and most of the time I don't even think about it, but the conversion factor, which of course is where you solve for 1, you say, well, 1 Newton for every 1 kilogram meter per second squared. Now that's okay. I would suggest it's a little easier to move this second squared to the numerator because it's the denominator of the denominator, so that means for every Newton second squared, there is 1 kilogram meter, right? Now let's talk about the English equivalence there. So 1 pound force, that's the unit of force. 1 pound force is the result of 1 slug being accelerated at 1 foot per second squared. Right? Now, how much is a slug? I don't know. I don't think in slugs. I think in pounds. So I think in pounds, and I can convert to kilograms if I need to in my head. I don't know what a slug is. Right? You can go look it up. Again, you'll see it in some other texts. We won't see it much in this text. I just mention it because if you've had statics or strength of materials or some other courses, you may have seen slugs already. Again, the slug is the one that is 1-to-1 here, similar to what we see in the metric system. That means for if I've got slugs, feet, and seconds, and I need to extract pound force from that, well, that means 1 pound force second squared for every 1 slug foot. All right, so that's my conversion factor. Now, what we will use in this course is the pound mass. 1 pound force is the result of 1 pound mass being accelerated at Earth's gravity. Earth's gravity in the English set being feet per second squared. I'm sorry, 32.2. This should be 32.2 feet per second squared. It's like 32.174. Okay, so 32.2 feet per second squared. What that means is that my conversion factor, anytime I've got pound mass and I need to go to pound force, it's not 1-to-1. It is 1 pound force second squared for every 32.2 pound mass feet. Now, it's very rare you will see me underline, box in, and draw stars around something. Now, when I was taking notes in college, if my instructor said, you need to know this for the test, I would always pull my red pen out and I would put big red stars all the way around this thing. That's one thing I love my calculus professor taught me to do that. He said, whenever I tell you that this is going to be on the test, feel free to put big stars and underline it and box it. And it's not very often I do something like that. So when I do, you might pay attention. This is probably something you want handy when you're doing homework problems, especially when you're working tests. This is a conversion factor that you will need. You can find it in your text, but you want it handy. Okay? So, this is important. Okay. Have questions? Send me an email. Find me in the chat room. You can leave a comment there. I'll try to get back to comments too. Okay. All right, so I've got a whole bunch of terms in Chapter 1. They are important, but instead of having 5 or 6 hours of lecture video, and I don't in a regular face-to-face class, I don't have time to get to all of them. So in these PowerPoint slides, which you'll find in Canvas, those of you taking my course, those of you who have joined us as guests on the internet, welcome, but you won't have access to my PowerPoints. Anyway, there are some additional terms from Chapter 1. We probably won't get to them in these videos, but if we do, that's fine. We can talk about them. Let's continue on. Let's talk about the terms we absolutely have to talk about. Right? Terms we absolutely have to talk about to talk intelligibly about anything in this course. The first one is the system. Right? The system. Remember back here when I said the first law refers to a system. And the second law also refers to a system. The first law refers to a system. Change in energy of the system with respect to time. What does that mean? Well, the system, and by the way, if you see direct quotes on my notes or in my PowerPoints, those are direct quotes. If there's no other source, that's a direct quote from your textbook. That is Thermodynamics by Chingle and Bowles, and I forget the third author that they've added in the new edition. If it's another source, I will give it to you. Okay. But anyway, they define very vaguely a system as a quantity of matter or region in space chosen for study. Now that's okay. Does this? I don't remember if a stylus works. No, it does not. So I would suggest anything we can isolate from its surroundings, right? And I don't have room to write that there. Anything we can isolate from its surroundings. In layman's terms, I remember my thermo professor taught us anything we can draw a dotted line around. That can serve as our system. Which can literally be anything. It can be huge, it can be tiny, but anything that you can isolate from the surroundings with an imaginary dotted line, that serves as your system. Okay? And our goal, again, as you see from this expression back here, our goal is going to be, if we look at everything that comes into, all the energy that comes into and goes out of the system, then that has to represent the change, because that energy must be conserved. By the way, mass will also have to be conserved, and other types of quantities can be conserved. So if I've got a system and I've established a boundary, then I'm really just concerned about what crosses the boundary, and does that equal the change. Right? So, to go along with that, some other definitions here. So if my system is just something that I can isolate from its surroundings to study it, that means I need something to make that isolation. The boundary is what we call the real or imaginary surface that separates the system from its surroundings, the surroundings being anything outside of the system. Now the boundary can be real or imaginary. If I want to consider my body a system, then my skin serves as a really good boundary. But just kind of like in your calculus class, how thick is a line or how big is a point, right? How thick is a line or a curve in a calculus course? Well, it's infinitesimally thin, right? It's only as big as you can as you have to draw it, right? And that's just a representation. So if I use my skin as my system boundary, it's really the infinitesimally small space right at the edge of my skin there. It's not actually my skin that I'm using as my boundary. I'm just using that as kind of a marker. And your boundary, again, can be imaginary. I can just say, let's just look at this little block of air right here that I'm circling around with my pen with an imaginary dotted line. That can also serve as my system. So again, we can use a real or imaginary boundary, but anything we can represent with a dotted line, anything inside that can serve as our system, and anything outside that can serve as our surroundings. Okay? So again, boundary can be moving. Boundary can be moving. It can be expanding. And we will see systems where the boundary is expanding. It has no real thickness, just like a curve or a line in a calculus class or an algebra class. Okay, two types of systems. Right. So we're going to deal with two types of systems. We're going to deal with what we call the closed system. The closed system consists of a fixed amount of mass. No mass crosses the boundary. All right. Now, what you've got here is one type of closed system we will often see is what we call the piston cylinder. All right. I'm going to have to stop there. So you guys are going to hear a pop. And we'll pick up on the next video.